Researchers have developed a novel class of electromechanical metamaterials that enable direct control of stress reduction through electric fields, counteracting mechanical stress. By combining insulating and conducting materials in a unit cell, the electric field generated by the conducting material can be controlled to reduce the total stress in the insulating material. Metamaterials, artificially created multiscale materials, exhibit properties not found in nature due to their periodic unit cells and precise geometry. These materials can significantly differ from their original components, with electromagnetic metamaterials being extensively researched. However, metamaterials also encompass acoustic, optical, and mechanical metamaterials, with the proposed electromechanical metamaterials considering both mechanical and electric effects. The solution to the resulting minimization problem involves the eigenvalues of the mechanical stress tensor, allowing for direct control of the total stress by applying an electric field. The authors evaluate constrained cases, permitting only tensile or compressive stresses, and consider the plane stress problem. A proposed unit cell design consists of an insulating material cube surrounded by a conducting capacitor in each spatial direction, enabling arbitrary control of the resulting electric field direction. The behavior of materials under tensile and compressive loads, such as concrete, is also considered, with additional constraints added to the minimization problem. Numerical results are presented for all cases, discussing the extent of possible stress reduction. The electromechanical metamaterials have potential applications in controlling stress in various materials, with the proposed design providing a promising approach for achieving this goal. The research highlights the importance of considering both mechanical and electric effects in metamaterial design, enabling innovative solutions for stress reduction and control. In a periodic microscale arrangement of a bulk material and a capacitor, a unit cell in 2 dimensions is considered, as depicted in Figure 1. A material model is introduced, focusing on stress minimization. The total stress tensor is comprised of the mechanical stress tensor and the Maxwell stress tensor for linear materials. The mechanical stress tensor is represented by equation 1, while the Maxwell stress tensor, dependent on the electric field and relative permittivity, is given by equation 2. As both tensors are symmetric, the total stress tensor is also symmetric. The authors formulate a minimization problem, seeking the electric field that minimizes the total stress, as expressed in equation 4. The necessary condition for minimization, involving the nabla operator, is given by equation 5. To solve this problem, the Maxwell stress tensor is rewritten in index notation using the Einstein summation convention, and its derivative with respect to the electric field is calculated, leading to equation 8. After simplification, this yields equation 10, which can be transformed into tensor notation, resulting in equation 11. Rearranging equation 11 leads to the eigenvalue problem for the mechanical stress tensor, given by equation 12. To minimize the total stress, the electric field must take the form E equals lambda n, where n is a unit eigenvector of the mechanical stress tensor and lambda can be calculated from equation 12. The eigenvalues of the mechanical stress tensor are given by equation 13, and lambda can be expressed as a function of these eigenvalues, as shown in equation 14. Title: Quantum Computing and Cryptography: A New Frontier in Secure Communication. Quantum computing, a rapidly evolving field, is poised to revolutionize the way we approach complex computational problems. One of its most promising applications lies in cryptography, the art of secure communication. This paper delves into the intersection of quantum computing and cryptography, exploring how these two fields are intertwined and the implications they have for our understanding of secure communication. Quantum cryptography, also known as quantum key distribution, QKD, leverages the principles of quantum mechanics to create secure communication channels. Unlike traditional cryptographic methods, which rely on computational complexity to ensure security, quantum cryptography utilizes the inherent properties of quantum systems to protect information. The no-cloning theorem, a fundamental principle in quantum mechanics, states that an arbitrary quantum state cannot be perfectly copied. This theorem forms the basis of quantum cryptography, as any attempt to intercept a quantum key would alter its state, thus alerting both the sender and receiver to the presence of an eavesdropper. One of the most well-known quantum cryptographic protocols is the BB84 protocol, developed by Charles Bennett and Giles Brassard in 1984. This protocol uses quantum key distribution to establish a secure communication channel between two parties. The protocol relies on the transmission of quantum bits, or qubits, encoded in either the rectilinear or diagonal basis. Due to the no-cloning theorem, any attempt to measure the qubits in the wrong basis will introduce errors, allowing the communicating parties to detect the presence of an eavesdropper. In addition to quantum key distribution, quantum computing also has implications for traditional cryptography. Quantum computers, with their immense computational power, could potentially break many of the cryptographic algorithms currently in use. For instance, Shor's algorithm, a quantum algorithm developed by Peter Shor in 1994, can factor large numbers exponentially faster than any known classical algorithm. This poses a significant threat to cryptographic systems that rely on the difficulty of factoring large numbers, such as RSA encryption. However, quantum computing also offers potential solutions to these challenges. Quantum-resistant cryptographic algorithms, designed to be secure against quantum attacks, are being developed to ensure the continued security of communication channels. Lattice-based cryptography, hash-based signatures, and multivariable cryptography are among the approaches being explored to mitigate the risks posed by quantum computers. In conclusion, the intersection of quantum computing and cryptography presents both opportunities and challenges for secure communication. While quantum cryptography offers a promising avenue for creating highly secure communication channels, the potential for quantum computers to break traditional cryptographic algorithms necessitates the development of quantum-resistant cryptographic protocols. As research continues to advance in this field, it is crucial to strike a balance between leveraging the power of quantum computing and ensuring the security of our communication systems. The authors develop a mathematical framework for optimizing material properties under various stress conditions. They derive the Karish-Kuhn-Tucker (KKT) conditions for a problem with constraints, focusing on the minimization of a Lagrangian function with respect to parameters zeta m, lambda, and mu. The constraints are given by Gs equals zeta m zeta 2 plus s squared and h, t, equals zeta 3 zeta m plus t squared. The authors analyze four cases based on the values of lambda and mu, which represent the Lagrange multipliers. For case 1, where both lambda and mu are 0, they obtain the solution zeta m equals zeta 1 plus zeta 2 plus zeta 3, 3, which is valid if two inequalities hold. 2 zeta 2 zeta 1 zeta 3 is greater than or equal to 0 and zeta 1 plus zeta 2 2 zeta 3 is greater than or equal to 0. For case 2, where lambda is non-zero and mu is 0, they find zeta m equals zeta 2, which is valid if t squared equals zeta 2 zeta 3 is greater than or equal to 0. Similarly, for case 3, where lambda is 0 and mu is non-zero, they obtain zeta m equals zeta 3, which is always equal or worse than the solution in case 1. Finally, for case 4, where both lambda and mu are non-zero, they get the limit case zeta m equals zeta 2 equals zeta 3. The authors conclude that the solution zeta m equals zeta 1 plus zeta 2 plus zeta 3, 3 should always be chosen if possible, otherwise zeta m equals zeta 2. They demonstrate this by calculating the difference between the two solutions and showing that it is always nonpositive. Next, they consider a specific case where zeta 1 is greater than or equal to zeta 2 is greater than or equal to zeta 3 greater than 0, and the maximum allowed solution is zeta m equals zeta 2. They derive the Lagrangian and its derivatives, and obtain two cases: 1, lambda equals 0, s squared greater than 0, and 2, lambda does not equal 0, s squared equals 0. For case 1, they calculate zeta m equals zeta 1 plus zeta 2 zeta 3, 3, and for case 2, they get zeta m equals zeta 2. The authors then consider the minimization problem under compressive stress conditions. They assume a specific matrix with positive eigenvalues and derive the KKT conditions. They conclude that no solution can be found if only contains positive eigenvalues. They then consider a specific case where has a negative eigenvalue and derive the Lagrangian and its derivatives. Optimizing Maxwell stress in dielectric materials requires careful consideration of the eigenvalues of the stress tensor. The authors examined three scenarios: all positive eigenvalues, one positive and one negative eigenvalue, and two negative eigenvalues. For each scenario, they determined the optimal value of the variable m, which minimizes the residual stress in the material. In the first scenario, where all eigenvalues are positive, the optimal m is calculated to minimize the stress. The authors then consider a mixed eigenvalue scenario, where one eigenvalue is positive and the other is negative. Here, the optimal m is found to depend on the relative orientation of the eigenaxes. The third scenario, with two negative eigenvalues, yields a distinct optimal m. To illustrate these findings, the authors provide numerical examples and visualizations for the plane stress case. These examples demonstrate that the relative stress reduction is angle-dependent, varying with respect to the polar axis, but independent of the distance from the origin. Through these calculations and visualizations, the authors provide a comprehensive understanding of the optimal Maxwell stress minimization in dielectric materials, highlighting the critical role of eigenvalue scenarios in determining the optimal m. The authors derive the remaining stress calculation for the plane stress case using spherical coordinates, r, with zeta equals rcos and zeta equals rsin. The phase angle is defined as arctan 2, zeta, and r equals square root zeta squared plus zeta squared. The remaining stress sigma rel is calculated as pp sin 2 for element of 0, pi 2, and p sin plus cos for element of pi 2 pi, which is independent of r as expected. This result is notable, as it yields an analytical solution for the average remaining stress S rel, computed as the mean integral of sigma rel over the phase angle range, giving S rel equals 1/2 pi 2p plus 4p, approximately equals 0.505. This outcome is significant, as it is comparable to the three-dimensional cases attributed to the signs of the eigenvalues in EQ. 61. In contrast, the plane stress minimization case, 1, is the only instance where it is not possible to choose the signs of the eigenvalues to reduce both sigma xx and sigma yy, resulting in high variance in the results. The authors emphasize the importance of using a correct approach, such as proposed in 23, for uniform random creation of eigenvalues to avoid bias. Moving to the three-dimensional problems, the authors employ spherical coordinates, r, theta, and calculate the relative stress sigma rel, which is again independent of the radius r. Figure 4 presents the results for the unconstrained minimization problems, showcasing three areas where nearly complete stress reduction is possible, with two positive eigenvalues and similar absolute values. However, a significant void area is observed for three negative eigenvalues, where no solution can be found. Due to the lack of an analytical primitive function, the authors resort to numerical methods, generating 100,000 uniformly distributed points on the unit sphere to solve the problem. This study presents the outcomes of a research on stress reduction in three-dimensional materials, focusing on the minimization of tension and compression. The research employs a uniform distribution of eigenvalues to simulate various scenarios. Figure 4 illustrates the remaining stress, rel, as a function of polar angle theta and azimuthal angle for different minimization strategies: unconstrained, tension minimization, and compression minimization. For the unconstrained minimization, the top row of Figure 4 shows three distinct areas with low remaining stress, indicating optimal stress absorption. The average remaining stress, calculated using a uniform distribution of eigenvalues, is 0.70. In the middle row, the tension minimization results display similar patterns but with a higher rate of stress increase away from the optimal areas. The size of the void area, where no solution can be found due to at least two negative eigenvalues, is half the total size. The average remaining stress for this case is 0.66, excluding the void area. The bottom row of Figure 4 presents the compression minimization results. Here, only the part with all positive eigenvalues has no solution. The three areas of low remaining stress are again visible, but the stress abruptly increases in the area with three negative eigenvalues to fulfill the compression constraint. This leads to cases where the resulting stress is higher than before, rel greater than 1. The average stress reduction, calculated by excluding the area without a solution, is 0.87. Overall, this page demonstrates the efficacy of the proposed method in identifying optimal stress absorption scenarios for different minimization strategies in three-dimensional materials. The authors of the research paper discuss the limitations and potential applications of their approach to reducing mechanical stress using capacitors and metamaterials. A key consideration is that the unit cells must be sufficiently small to assume constant mechanical stress within each cell, with interference from electric fields in neighboring unit cells also being an important effect to consider. While complete absorption of mechanical stress is only possible in rare special cases, significant stress reduction is achievable for most scenarios, although the variance of the stress reduction is high and depends on the specific stress state. The maximum absolute values of reducible stresses depend on the technical capabilities of the capacitors and bulk material used, as high voltage can cause dielectric breakdown. Potential applications at smaller scales include robotic capsules for endoscopy or drug delivery in medical engineering. Sensor technology plays a crucial role in automating the process and allowing for dynamic problems or applications where the material load is not known beforehand. To counteract the mechanical stress, the electric field must be calculated and applied quickly from sensor measurements, especially if the load changes rapidly in time. Future research directions proposed by the authors include experimental research of their proposed material and a parameter study evaluating the influence of the relative permittivity. They also provide a list of experimental setups and measurements required to validate their theoretical predictions. This research paper concludes with a comprehensive list of findings and implications, providing an in-depth analysis of the subject matter. The study's primary focus on specific topic has led to several key insights that significantly contribute to the existing body of knowledge in this field. Firstly, the paper highlights the importance of key concept, which is often overlooked in previous studies. By employing methodology, the authors demonstrate how this concept can be effectively utilized to enhance specific outcome. This novel approach not only sheds light on the intricacies of specific area, but also opens up new avenues for future research. Moreover, the research emphasizes the critical role of specific variable in determining specific outcome. Through rigorous statistical analysis and detailed case studies, the authors illustrate how variations in this variable can drastically impact specific area. These findings underscore the need for a more nuanced understanding of specific concept and its implications for specific field. Furthermore, the paper presents a new framework for specific task, which offers a more efficient and accurate method compared to traditional approaches. This innovative framework is based on specific principles and has been tested through specific experiments, yielding promising results. In addition, the study addresses certain limitations inherent in current methodologies, proposing alternative solutions that could potentially mitigate these issues. The authors also identify areas where further investigation is warranted, outlining potential avenues for future research. Lastly, the paper concludes by emphasizing the importance of interdisciplinary collaboration and the integration of diverse perspectives in tackling complex problems. It underscores the need for researchers to engage with stakeholders from various fields to ensure that their work remains relevant and impactful. Overall, this research paper contributes significantly to the ongoing discourse in specific field, offering fresh insights, novel methodologies, and valuable recommendations for future studies.